Today, we're diving into a fascinating scientific detective story. Our mission? To uncover the secrets of a super catalyst that could completely change how we make some of the most common materials all around us. So let's jump right in.
All right, here's our game plan. We'll start by looking at the challenge we're trying to solve. Then we'll meet our mysterious catalyst. We'll follow the clues piece by piece, and finally, we'll crack the code and see why this discovery is such a big deal for the future.
You know, every great mystery needs a motive. And in the world of industrial chemistry, the motive is usually pretty simple. Figuring out how to turn something cheap and easy to find into something incredibly valuable. So what is this valuable stuff we're after? It's called acrylic acid. Now, you've probably never heard of it, but trust me, it's a crucial building block in your life. We're talking about everything from super absorbent polymers in diapers to coatings, adhesives, and tons of plastics. It is literally everywhere.
Okay, so here's the puzzle that chemists have been trying to solve for decades. How do you take a simple, common gas like propane and efficiently turn it into this complex, super valuable acrylic acid? It's a tricky chemical journey, and to make it happen, you need the perfect guide. And that guide is a catalyst.
And that brings us to the main character of our story. It's a material with a pretty complicated name, but it has some truly extraordinary abilities. Let me introduce you to MoV10 box. Yeah, it's a mouthful. Just think of a catalyst as a kind of chemical matchmaker. It brings different molecules together and helps them react, all without getting used up in the process. This specific one is a complex crystal made from 4 different metal oxides, and it's shown some incredible promise for that propane to acrylic acid conversion. And here it is, our first look at the subject under a microscope. You can see it has this really distinct, rod-like shape. But seeing it just brings up more questions, right? What is it about this specific structure that makes it so darn good at its job? That's the mystery we're here to solve. Now, the first big clue came from a place nobody really expected. Scientists noticed that the reaction worked amazingly well under one specific condition, but it completely failed without it. And that secret ingredient was just plain old steam. So the investigators asked a really simple question. The process normally uses a ton of steam. So they thought, okay, what happens if we just take the steam away? And the result was, whoa, it was dramatic. As you can see from this chart, with steam, the catalyst was cranking out a high yield of acrylic acid. Awesome. But without steam, the yield just plummeted. The performance literally fell off a cliff. This was a huge discovery. Steam isn't just hanging around. It's playing an active, absolutely vital role. But what is it doing? To answer that, scientists had to look deeper. I mean, way deeper. They needed to see what was happening to the catalyst while the reaction was happening, and that required some seriously powerful technology. They used a technique called in situ X-ray analysis. The best way to think about this is like giving the catalyst a live CT scan while it's in the middle of working, at 400 degrees Celsius, surrounded by all these reactive gases. It lets you see if the fundamental structure, the very skeleton of the material, is changing. And the results were pretty stunning. The internal structure, it was rock solid. Even when they took away the steam or messed with the gas mixture, the core of the catalyst didn't change one bit. This was a massive clue. It meant the chemical matchmaking, the real magic, wasn't happening deep inside the crystal. It had to be happening somewhere else. So they turned to an even more powerful tool, a scanning transmission electron microscope. And this is the aha moment right here. On the left, you see the catalyst before the reaction. It's all smooth and solid. But look at the right. After the reaction, its surface is completely transformed. It's covered in these tiny pits and voids. The inside stays the same, but the surface becomes this dynamic, pockmarked landscape. That is where the action is. Okay, we have our clues. A super high-performing catalyst, the fact that steam is absolutely critical, a core that's stable as a rock, and a surface that's constantly changing. Now, let's put it all together and solve this thing. First, let's just simplify the chemistry a little bit. This reaction doesn't happen all at once. First, the propane gas lands on that active surface of the catalyst. Then it gets converted into something else, an intermediate product called propylene. And finally, that propylene is quickly transformed into the acrylic acid we're looking for. And here it is, the solution to our mystery. The absolute genius of MoV10 box is that it has this dual nature. It has an incredibly stable core that acts as a tough foundation, so it doesn't just fall apart. But its surface is dynamic and always changing, creating the perfect little spots for the reaction to happen. And the role of steam? Steam acts like a bodyguard, protecting that delicate surface, preventing it from getting damaged and allowing it to do its job over and over and over again. So, we've solved the case of this one super catalyst. Pretty cool, right? But what does this all mean for the bigger picture? Why does understanding this one single material matter so much?
Well, let's just look at the numbers for a second. This table compares our Move-10 box catalyst to some of its predecessors, and the difference is just staggering. I mean, look at that. Older catalysts might convert about 15 to 20% of the propane and get a tiny 3% yield. This new material? It gets a 56% conversion with a massive 44% yield. That's not just an improvement, it's a total game changer.
And this right here is the real takeaway. By cracking the code of how this one catalyst works, by understanding the importance of having a stable core and a dynamic surface, scientists now have a blueprint. They can use these exact same principles to design a whole new generation of catalysts for all sorts of other important chemical reactions. We're talking about making manufacturing processes more efficient, less wasteful, and ultimately a whole lot greener.
And that leaves us with one final, really tantalizing thought. If a catalyst this smart can revolutionize how we make plastics and paints, what other massive global challenges, from creating sustainable fuels to cleaning up our environment, could the next generation of super catalysts designed with this very blueprint help us solve?